Hello everyone. This presentation is about implementation of a neoteric clustering approach in wireless sensor networks domain. We'll be using spectral clustering and residual energy concepts in the following presentation. My name is Sankat Mohanty. I'm a graduate student at the University of Florida. Let's start with the outline of this presentation. It is subdivided into three sections. First one deals with spectral graph partitioning. The next one is about spectral clustering, and the third one is about the algorithm itself that has been implemented in wireless sensor networks. In spectral graph partitioning, we'll be going for a very experimental program that will simply partition a graph using second smallest eigenvector concepts. We'll be following through with the MATLAB outputs and finalizing our observations from it. In spectral clustering, we will be more into a graph partitioning point of view, where we will analyze ratio cut and normalized cut algorithms, and we will find the results and observations related to them. Finally, the major part of this presentation deals with a new type of algorithm known as a K-Way Spectral Clustering Algorithm. We will deal with the motivation behind this and the entire spectral clustering scheme that has been employed. Then we will finalize some evaluation metrics, and then after doing several simulations and observations relating to it, we will draw some corresponding conclusions. Finally, the summary of the entire presentation is derived. Let's start with the very first subsection known as the spectral graph partitioning, where we'll implement a simple experimental approach. We all know what a graph partitioning is, and here in this segment we will plan a partition in the graph and then use the second smallest eigenvector to find it. As always, the very first step is to generate our data set. In my program, I have used a large number of vertices, like almost n is equal to 1000 vertices. Then the second step employs to plant an artificial partition in our dataset. So we need to determine the number of vertices in each of the groups. To do this, we randomly generate a permutation of all the vertices and select one set as group 1 and the rest as group 2. Now next we need to decide the probabilities of edges within each group and between the two groups. Because we are planting a partition, the probabilities of edges between the groups should be much lower than the probabilities of edges within each group. Suppose that the group 1 is a little more tightly connected than the group 2, we can have our own formulations. With these probabilities in hand, we can then construct our graph, and the next few operations will be to symmetrize the matrix. Now let's see what we get as outputs from this following program. After symmetrizing the matrix, this is the very first plot we get in MATLAB, which is the initial graph set of random points, and there is no visible partitions in this. Moving forward, we find out the second eigenvector v2 and we plot it. This is what the plot we get. But this is also not that much helpful. Maybe when we sort the vector, we can find something better. After sorting the vertices and plotting them, we get this structure. We can see a large gap in the middle of the values. Interestingly enough, the number of points on the right of the gap is same as that of the size of the planted group. Now let's see, when we permutate these vertices of the graphs to this ordering, what do we get? This is finally what we get as the final partitions of the graph, and it's clearly visible as the final partitions of the graph.